Okay, we're going to look at some web assign problems. This first one says the student stands on a bathroom scale in an elevator that's at rest on the 64th floor of a building. The scale reads 849 newtons. As the elevator moves up, the scale reading increases to 931 newtons. Find the acceleration of the elevator. So let's draw a diagram. There's my elevator. There's my scale. And the person is standing on the scale. The weight of the person is straight down, and that's Fg, and that was given in the problem as 849 newtons. The normal force is actually what's being read by the scale, so I'm going to write Fn and F scale, and they told us that was 931 newtons. Our goal is to find, let's go back to the question, the acceleration of the elevator. So we're trying to find A. Now, because the weight is equal to m times g, I would like to use that to find the mass of the person. So mass is equal to the weight divided by acceleration due to gravity. So we have 849 newtons divided by 9.8 meters per second squared. And your weight of this student is 86.6 kilograms. We'll need that a little later. All right, now we're trying to find the acceleration of the elevator. So looking at my summation of forces, that's going to accelerate my student. So in the downwards direction, I have weight. In the upwards direction, I have the normal force. Up is positive, down is negative. So I'm going to say Fn minus the weight will give me the acceleration on the system. So we know Fn, we know Fg, and we know m. So rearranging my equation, I have the normal force minus the weight divided by m will give me my acceleration of the elevator. Fn is 931 newtons. The weight is 849 newtons divided by 86.6 kilograms. The acceleration of our elevator is 0.947 meters per second squared. It's positive, so that means the acceleration is in the upwards direction. All right, let's look at another problem. This one says a crate weighing 582 newtons is resting on a plane inclined at 34 degrees above the horizontal. Calculate the magnitude of the acceleration. So here's our inclined plane. The angle is 34 degrees. We have this crate on it. Now they give us the weight of the crate. Fg is 582. Since they want the acceleration, I just know we're going to need to know the mass of it. So remember, Fg is equal to m times g. So to find the mass, we're going to take weight divided by the acceleration due to gravity. Oops. Let me clean that up. So Fg, 582, 9.8 is the acceleration due to gravity, and the mass of this crate is 59.4 kilograms. .4 kilograms. Okay, let me show you some forces. Weight, straight down, Fg. Now, pretend you have a XY coordinate system and it's centered on the center of mass of this box. So there's your X direction, and there's your y direction, and that's going to be my Fy, which is equal to, on an inclined plane, the normal force. Along the incline or parallel to it, that's your Fx. Remember, that can also be drawn right there. That can be our Fx. So remember, the interior angle is the same as the angle of your inclined plane, so it's 34. We need to find Fx, because if we look at all the forces in our plane, let's look at the summation of the forces to accelerate our box down the plane. Only thing acting parallel to the plane is f of x. So if we can calculate f of x, we'll have the force we need. So f of x is going to be, if we calculate the sine of 34, it will equal f of x over fg. Fg is always the hotness. So let's go to the next page, and we write that in a general format. Sine of theta is equal to f of x over f of g. For r's, f of x is going to equal f of g sine theta. Now for r's, it's 582 newtons times the sine of 34 degrees gives us a value of f of x of 325. That's the only force acting on the box. So going back to our f of x equals mass times acceleration. Trying to find a, so f of x over a is equal to, that should be mass, 325 newtons over the mass of the crate was 59.4 kilograms. The acceleration is 5.48 meters per second squared down the inclined plane. Okay, I'm going to stop there and I'll do one more problem on a different film, but I got to make sure I don't run out of time.